Okay, so for this video, I'll go through Boyle's, Charles, Gay-Lussac's, and the combined gas law. I'll make a separate video for the ideal gases, Dalton's law of partial pressures, and the rate of diffusion. So this one's only going to cover Boyle's, Charles, Gay-Lussac's, and the combined gas law. So if we start with Boyle's law, and you will definitely need to know the name of the law that goes with the equation. So Boyle's deals with pressures and volumes. So P1 V1 equals P2 V2. Okay. Now the ones and the twos, what do those stand for? Well, the one stands for the initial volume, initial pressure. So they may give you some initial conditions, and then the two stand for the final volumes or final pressures. Okay. Now Boyle says that pressure, and I'll write it here, pressure and volume are inversely related. So what does inversely related mean? Well, what that means is as one of them increases, the other one decreases, or vice versa. So if we were to increase the pressure, so imagine squeezing something or pushing down on a balloon, then what actually would happen is we're forcing it into a smaller space, so the volume would decrease. So if we're pushing down on something, we're forcing it into a smaller volume. So you notice they go in opposite directions. Likewise, if we were to decrease the pressure, so if we start to take, if we're squeezing something and we start to gradually stop squeezing it, then we're allowing for the volume to increase. So all you really need to keep in mind is that pressure and volume go in opposite directions. Okay? So if the pressure of something is increasing, that means the volume must be decreasing. The gas must be in a smaller space. Okay? Remember, pressure is all about collisions. So the more collisions, and I'll write that up here. So more collisions equals higher pressure. Okay? So if you think about being in a tight room with a lot of people, you might bump into each other a lot more often. That's creating more pressure or more collisions. Same idea with a gas. So a gas in a smaller container, it's going to hit the container and hit other gas particles more often than if it's in a larger container or a larger volume. It's going to be more spread out. It's not going to hit things as often, so it's not going to be as much pressure. Okay? So that's Boyle's law. If we were to graph this, just as a little sketch, let's say this is pressure on this axis, and let's say this is volume on this axis. It would look something like this. Okay? As one increases, so as the pressure gets bigger, the volume is actually decreasing. Okay? Inversely related, they go in opposite directions. Okay? Charles' law. Put it over here on this part of the board. So Charles' law. One way to kind of memorize this is Charles. We could say Charles went to VT or went to Vermont. So Charles went to VT may be a way to try to remember this. So this is V1 over T1 equals V2 over T2 for Charles' law. Again, the V1s and T1s, those are your initial conditions or initial volume, initial temperature. V2 are your final volume, final temperature. Okay. Charles says that volume and temperature are directly related. So not inversely this time, but directly related. Well, directly related means whatever you do to one has the exact same effect on the other. So if we were to increase the temperature, the volume should increase. If we were to decrease the temperature, the volume should also decrease. So they go in the same direction. If we were to graph that, and I'll try to stick it over here, if we were to graph it, let's say we put volumes here, or volume here, and temperature here, it would look like a line like this. As you increase the volume, the temperature increases. Or vice versa, as we go this way and decrease the volume, the temperature is also decreasing. So again, directly related, they go in the same direction. So volume and temperature are directly related. But if we switch back over here, Boyle says pressure and volume are inversely related. So let me give you a real world example for Charles' law. So if we were to, let's say, put a marshmallow in the microwave and we heat up those particles in the marshmallow, or even if we bake a cake, we're heating up those particles in the cake pan, the volume is going to expand. The container is going to increase the volume. If you were to actually take a balloon and put it outside since it's cold enough, or to put it in a freezer, you're cooling down those gas particles. They're going to slow down. They're not going to move as quickly, and the volume of that balloon is going to decrease. All right, so I'll stick the last one on this part of the board. This is Gay-Lussac's. So Gay-Lussac's law, and his deals with pressures and temperatures. So it's set up very similar to Charles's law, but it uses pressures and temperatures. So P1 over T1 equals P2 over T2. Okay? So according to Gay-Lussac, pressure and temperature are directly, just like with volume and temperature, they're directly related. Okay, and again, we said that directly related means they go in the same direction if we were to change them. So if we were to increase the temperature, the pressure also increases. Okay? And vice versa. If we decrease the temperature, the pressure would also decrease.